Hello, welcome to the second day of 3.2. Today we're going to learn about residual plots, R squared, but most of the day we're just going to have problems that you're going to work or we're going to work on together, and you'll see how to do some of these problems here. All right, first thing we want to talk about is we're going to look at the problem that we looked at yesterday with knee height and height, and trying to predict the height of elderly people. And the first thing we're going to do with it is we're going to build a residual plot. A residual plot is a scatter plot of the regression residuals against the explanatory variable, or equivalently against predicted y values. The residual plots help us assess whether a regression line fits the data. So basically, when we graph our residual plot, we're going to have our x values over here. Values, hopefully I can spell. And over here, we're going to graph the residuals. So the residuals are going to be the y, the x values are going to stay the x. Now here is an example. And remember last week we had y hat, or yesterday, y hat equals 2.34x plus 48.11. This is our least squares regression line for this data. So we can go in here and we want to find the expected value for each of these. To do this, what we need to do is put in this x value in here. So 2.34 times 56.7 plus 48.11. And if I did that, I got 180.9. I'll move that so it's a little easier to see. All right, now we're going to do the same with the rest of them. So if I plug in 47.4, I get out 159.15, let's just say 0.2. And then my next one, if I plug in 43 and a half, I get 150, pretty much even. Then if I plug in 44.8, I plug in 153.1, $177.4 is that one. So now, what I want to do is look at this graph. Or this table, and I want to figure out my residuals. What we'll do is we'll take the height minus our expected value to find each residual. So we just have to subtract those numbers. And again, I'm going to get 8.16, negative 5.85, negative 3.62, 9.64, and then finally negative 8.33. I should probably move that over a little bit so you can all see it. So those are our residuals. So we have our y-axis. Now my x-axis is going to be right in the middle here. So our x-axis is going to be the same values that it was over here. So we're going to start with 40 and go up to 60. See if I can type small numbers in here. So 40, and then over here we went up to 60. And now we have to think about our scale for our residuals. Well, it goes all the way up to 9.6. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, this would be a good scale here. We can just go from 10 all the way down to negative 10. So those are residuals. And let's put a few more markings on here. 40, 41, 42, 43, 44, 45. And we have 46, 47, 48, 49, 50. That's right there. And then we'll get 51, 52, 53, 54, 55 right in there. And that'll help us with our graph. So now we just have to plot the points. So we're looking at the knee height and the residuals. So at 56.7, over here, it's going to be 8.61, 8.16. So it's somewhere around here. 47.4, which is about there, it's going to be negative 0.58. So I'm guessing somewhere around there. 43.5 is going to go up to negative 3.6, so there's negative 3. 3.6 is somewhere there. 44.8 is going to go up to 9.64. And 55.2 is going to go up to negative 8.33. So there's the graph. This is what we call a residual plot right here. Now we should label the points. This or the axes. This is knee height. I don't know why I'm trying to do this without typing it. I just have my mouse today, so no fancy writing. And then over here we'll have just write residuals. All right, here we go. Now residual plots, what we look for is not showing any obvious pattern, and the value should be pretty close to the predicted value. So mainly we should just look for number one. If these residuals had some curve to them, we could say that maybe it's not a linear, a good regression for a linear function. But since this seems to have no pattern whatsoever, this looks pretty good. Now, some examples that would show a linear pattern. So if we have a scatter plot that looks like, oops, if that's my residual plot, that doesn't seem to have any pattern whatsoever. So that would show that the regression line would be linear. And it doesn't have to be exactly perfect. Something like that would be good enough to say that the regression line is fine. When you have fewer and fewer points, here it's easy to see that it's scattered, but when you have fewer and fewer points, it's harder and harder to interpret, because without this point here, people could think that maybe it was a quadratic. All right, some shapes that would show a nonlinear pattern. You could have some sort of regression or residual plot like this. It shows that it's up, goes up, and then comes down. That would show a nonlinear pattern. Or if there was some sort of line in it, then we would know it's a nonlinear pattern. So those would represent nonlinear, where the scattered residual plot shows that it would be a linear pattern. Now there's a way that you can tell, you can look at the standard deviation of the residuals to look at number 2, but we really don't get into that much until we get to chapter 15. All right, now we need to learn how to read Minitab printouts. Minitab is just one computer program that statisticians use to analyze data. And here is a printout. And also these are something that's they're common to see on an AP test. In this problem, Leonardo da Vinci, a renowned painter, has speculated that the ideal human would have an arm span that was equal to his height. The following computer regression printout shows the results of a least squares regression on height and arm span in inches. For example, 18 high school students ranging from 67 inches to 75 inches. Now we need to learn how to read this. Now the first thing we can look at is the dependent variable is height. So that's one thing we should see. So that's going to be our y variable. There's a constant, and then this variable arm span. So arm span is our other variable. So height is the dependent variable, so arm span must be our independent variable. These values right here, this gives you your slope, and the number above it gives you your y-intercept. So these are very important because you can just look at this and see your slope and y-intercept. Now, this data and these we learn about later. None of this stuff and degrees of freedom do we look at. We can find our r squared to be 87.1, and we'll learn more about that at the end. R squared adjusted, we don't pay attention to this one at all. And this S is the standard deviation of the residuals. So it just shows how closely, what the spread of the residuals is. All right, so in this problem, they ask us, find the slope of the regression line and interpret the slope in the context of the problem. So we could say slope equals 0.840424. Now, if we want to interpret this, we can say for each increase in in 1 unit of arm span, the total height increases 0.8404 units. That's what our slope means. So for every increase in a unit of arm span, the total height will increase that amount. Now let's find the y-intercept and interpret that in the context of the problem. So our y-intercept we found was up here. I thought I would help by seeing both sides, but I can't actually read it very well. How about I just copy and paste it over here? So our y-intercept is 11.0 11.54. What this means is when the arm span is 0, the total height is 11.5 units. Does that make sense? No, this doesn't make sense because uh, if someone's arm span is 0, the distance from the tip of their fingers would be 0, then it wouldn't make sense for them to be alive, nevertheless have any height of 11.54. All right, so now if we have those, we can write our least squares regression line, where I'll write y hat is equal to 0.840424 x plus 11.5474. Now we also have to define y. Y is the height, x is the arm span. Also, if something, what I should say, y is the predicted height. I'd actually get a point taken off on an AP test. And so on my test, if I didn't say predicted height. So you need a little y hat up here. All right. So predict the height of a person if the arm span is 59 inches. So we just have to plug in 59. So 0.840424 times 59. Oh, my calculator was kind of funny. I'll try that again. Times 59 plus 11.5474. I got 61.13 61.132. All right. Now here's an example 3. I want you to try this one on your own. Do the least squares regression line, find the meaning of the slope, interpret the y-intercept. And here's example 4. I want you to interpret the slope, interpret the y-intercept and the regression, and then draw a graph and predict the rat's weight. All right, so hopefully you've paused. I'm going to go through the answers at the end of the lesson. Now let's go to number 5. Here it says anthropologists must often estimate human remains, how tall the person was when alive. Carla's studying the overall height can be predicted from the length of leg bone in a group of 36 living males. The height shows that the bone lengths have a mean of 45.9 and a standard deviation of 4.2. The overall heights have a mean of 172.7 and a standard deviation of 8.14. And the correlation between the bone length and height is 0.914, where the scatter plot has a linear form. Find the regression equation. All right, now there's a formula. We talked about it once. It's not very common. It hasn't come up much. But we can find the slope if we know the correlation coefficient, standard deviation of y, and standard deviation of x. So let's fill in our values. It says the correlation is 0.914, so 1. And we're going to multiply that by standard deviation of y. So that's going to be the overall height, 8.14 divided by the standard deviation of our x's, which is 4.2. And if we do this, 8.14 divided by 4.2, now multiply that by 0.914, I get 1.77 for my slope. So my slope is 1.77. Great. So now I just need to find my equation. The means are always a point on here. So the mean 45.9, comma 172.7. Now that's a point on the line. Now if you know the slope, you know a point. Now can you guys take a second on your own and try to figure out what that line is? I'll tell you what the equation of the line is. At the end of the lesson, I'll show you the answer. All right. Now, also, can you guys try example number 6? And this has a lot to do with our previous problem, example 5. All right. Now, our last thing we need to learn today is the coefficient of determination, r squared. The coefficient of determination, r squared, is the fraction of the variation in the values of y that can be explained by the least squares regression line of y on x. We can calculate r squared, and usually what we do is we just take our r value and square it, and there used to be a formula, and I erased it because it was more confusing than enlightening. So we don't even need to deal with that right now. R squared usually says something like RSQ. So here we have that. R squared is 96.7. Now, in this one, our first question says, is a linear model appropriate for modeling this data? So if you look at our residual plot, is there any pattern? I don't see a pattern. So I would say something about how there's no pattern in the residual plot. There is no pattern. Now you have to be really careful with this. It says there's no pattern in the residual plot, so the original data is linear. Sometimes people say there's no pattern in the residual plot, so it is linear. And we don't want to say that the residual plot is linear, because this is definitely not linear. But if we look up here, the original data looks linear. So how much faith do you have in your regression line above? Well, the r squared is 96.7, and that's a really high number. So you can say pretty good faith. That's a pretty high, that's a strong correlation. Would it be reasonable to use the fitted regression line to predict fuel consumption on a route on this, for a train on this route, if a train had 65 rail cars? Now if we look up here, 65 rail cars, that would be outside of our data. So we don't have no idea what it would look like. We could estimate it, but since it's extrapolation, we'd probably be a little off. Do the slope and y-intercept have meaningful interpretations in the context? If not, state the interpretation. If so, state the interpretations and explain why. Well, the slope means that would be this value here is our slope. That means for every increase in one rail car, fuel consumption goes up by 2.1459. So that's a pretty reasonable slope. Our y-intercept would be if you have 0 rail cars, your fuel consumption is 10.7. Now, I'm not sure if that's reasonable. I wonder if rail cars are the ones behind the engine, because then maybe just the engine itself is 10.7 for fuel consumption, and every additional rail car adds more. It's not entirely clear from the problem. All right, that was a long lesson. Hopefully you got through it all right.